Um, we also do recognize other influences on fatigue life. For example, one of the main influences is if I have a crack, it does matter whether my stress variation is fully in compression or in tension. For example, you can see here you have the amplitude ratio. And here you have so here we have compression, and here we have tension. And you can see that if you are under compression, the stress variation is always at the same level. While if I increase the average tension, then the reduction of allowable stress variation becomes apparent. And not every standard takes that into account, but older standards like the DIN 50018 or the PEM grain standards, for example, they do take into account this compression stress and tension stress difference. And what is the cause of this? If I have, suppose I have here a material and I have an initial crack, what you calculate in the stress variation is the stress here at your tip, the delta sigma, and the failure mode of a crack here is when, of course, when a crack opens. Yeah, so if you stay under compression, if you have a stress variation, if we take here the stress, so this is delta, this is the stress, and this is time. If I stay here, I could say I always have a compression stress, so my tip does not open. Other standards, like the Eurocode, they do take into account this effect, but they do not use a curve like what you see here, but it is more a general rule. It states if I have a material which is under compression and it is stress relieved and it is not welded, then I can take, instead of the compression stress, I can take 60% of the stress under compression. So if I go from, suppose I go here, so the compression part is then only 60%. So that is effectively a reduction of your total sigma, because you only need 60% of this point. So instead of going all the way up till here, from here till there, my delta sigma is supposed to be slightly smaller. By the way, somebody knows why these rules are valid only for non-welded steel. And because if you weld, you have another problem. This reduction in welding is considered to be non-apparent unless you have stress relieved. And what is the reason of that? If I have here a material and I weld something here, what happens in this at this spot? Of course, a weld results in a stress concentration factor. So I have a lower fatigue limit because I already have a stress concentration, which so the peak stress the local peak stress is somewhat higher. That is 0.1. So I have stress concentration factor which is higher. The other thing is, during the welding process, this is molten material, and in the cooling down process, what happens? The weld shrinks. So if if I have here some kind of initial crack, I open the crack. Yeah, so I get, due to this shrinking, I get initial cracks at these tips, which are also, so I have initial cracks, which further reduce the strength. The third one, and that is important also for this compression stress method, is because this material shrinks here due to the cooling down. That means that at the surface I have a stress level which is yield, but then under tension because it shrinks until it plastically deforms. So I have here at the surface always tension up till the yield limit. So that means that my stress, even if I have over my global model a stress which is in compression, locally I still have the crack to be opened. And so that is the reason why for welds we do not take a reduction in of compression stress compared to tension stress, while for non-welded materials we do apply these rules. There's only one exception, and that is if you after welding reheat the full structure so that so that the tension stress which exists at every weld is then reduced to zero. Yeah, but that does not happen very often, especially not for ships and so on, because that is a huge amount of work to do that. Okay. So we have our rules where we can calculate fatigue damage and so on. But now we only have a curve. Now we have here a curve, but the main point is now what we need to determine is this delta sigma k. If this number is fixed, that one is fixed. This is 55% of the critical stress level. This is what we call the fatigue stress level, and that is in general or 10 million, 2 million, 1 million, depends a bit on the standard, but that is the number of cycles which did not result in failure after that number of cycles. You have to take into account that now we use vibration, for example, to create stress variations, but if you need rotations to find, or you need to rotate a part, or even worse, if I have a specimen, I have some kind of machine which needs to put under pressure and then no pressure, under pressure, no pressure. If you need to do that with an old machinery, that takes forever. So basically, when they started to do a lot of these fatigue measurements, forever was 1 million, 2 million. That sounds like almost forever. Yeah, so that's the reason why we had this critical stress here at this buckling point, at this critical stress value, which in the end turned out to be that if I have more than 2 million load cycles, I do still have some damage due to fatigue, but that is much lower with a lower slope. And then at 55% of that value, then even for loads above 10 million, that will not result in fatigue. By the way, this curve in this way is for steel. For aluminum, the last part is not present, because you always have, for every stress variation, you do have some damage accumulation. The same is, for example, if you have steel which is exposed to seawater, for example, due to the corrosion effect of salt water, you always have damage as well. So depending on the situation, this curve might slightly change, and also completely this plateau for infinite life might disappear.